Good evening, everyone, and welcome to our first class. And our first topic is Introduction to Probability Distributions. The concept of probability distribution is quite similar to a concept that you came across in Business Statistics 1, and that is the concept of a frequency distribution. So to start us off, I want us to have an illustration to consider a scenario here of a frequency distribution and how we can quickly convert it into a probability or into a simple probability distribution. So the illustration is, suppose you conducted a survey in a certain estate in Nairobi, and one of the variables that you are interested in was the number of children in the sampled households. So in this case, the variable of interest, that is the number of children in the sampled households, can be labeled as X. So we can say, let X be the variable of interest. And let's suppose, for the sake of illustration, let's suppose that X takes these values. The number of children, suppose some families have 0 children, others 1, 2, let's say up to 5. So I want to have some hypothetical data for the sake of illustration, as shown in the following table. So suppose this is the data that we collected from that survey. So this is an example of what we call a frequency distribution. This is a frequency distribution. Frequency distribution. And more specifically, this is called a discrete frequency distribution, because the variable under consideration here is a discrete variable. That is, X is a discrete variable. Okay. So we can quickly convert this table into a simple probability distribution as follows. But before we do that, let's recall the definition of the probability of an event A. And we know that probability of an event A is given by the number of times that A occurs divided by total number of occurrences in the sample space. Of course, in this scenario, we're assuming that the outcomes in the sample space are equally likely. They have equal likelihood. Okay, so for instance, we may want to find the probability that a given family has no children. If you want to find the probability that a given family has no children, you just come to the data given here and you check the number of times that X is equal to 0 is appearing. And in this case, it is appearing twice out of, so we need to get this total here. If you sum up these values, you'll get this is 40. So the probability that a given family in the estate that was surveyed has 0 children is 2 out of 40. And then the probability that X is equal to 1, that is, a given family has only 1 child, is 7 out of 40, and so on and so forth. So that means we can insert a column here, probability. So this will be 2 out of 40, 7 out of 40, 8 out of 40, 14 out of 40, 6 out of 40, and finally, we have 3 out of 40. When you sum these probabilities, you'll get 40 out of 40, or 1. When you sum all the probabilities, you will get 1. That is only true if the values of x that you put here have not left out any possible value of x. So that means if the values of x indicated in the table are exhaustive, then you're going to have this one sum up to 1. So now, if we were to remove this middle column here, if you were to remove this information here, you have to remove the middle column there, you will be left with what we are calling an example of a probability distribution. Okay, so let's extract that and see what we're going to end up with. So when we remove the middle column, we'll end up with a table similar to this. Okay, and this is an illustration, or this is an example of a probability distribution. So a probability distribution can be in form of a table like this one, or it can be in form of a graph like this one. So this is also an illustration of the same probability distribution. So this is also probability distribution. Okay. So basically, when we talk about a probability distribution, we refer to a table like this one, or a graph like this one, but sometimes we also have a formula which assigns probability values to all the possible values of x. Is a table or a graph like this one, or a formula which assigns probability values to all the possible values of the variable in question. And that's what I want us to write as the official definition of a probability distribution. So we're saying that a probability distribution is similar. It is very similar to a frequency distribution like this one. It is similar to this kind of table. But now we're saying that instead of showing frequencies, it shows probabilities. It shows probabilities. But more formally, we can say that probability distribution is a graph or a table or a formula that specifies the probabilities associated with all possible values of the variable of interest. Okay. When we talk about all the possible values, let me underline these. All the possible values of the variable of interest. The part I've underlined is actually the definition of what we call sample space in probabilities. So let's remind ourselves, recall the meaning of the word or the term sample space as used in probabilities. So we're saying that this refers to the set of all possible values of the variable of interest. And in our previous example, we can say that the sample space contains the elements 0, 1, 2, 3, 4, and 5. Okay. Then we can continue by saying that probability distributions can be broadly classified into two. That is, into what we call. So before we look at the definition of each of these two types of probability distributions, let's recall the definition of a discrete variable and also a continuous variable. And we say that a discrete variable is a quantitative variable whose data takes some specific numeric values. And in most of the cases, or most of the times, discrete variables take whole number values, but not all the times. Okay. For example, you can think of a variable like this, e.g., the number of students in different classes in KCA University. That's an example, because the number of students in every class will always be a whole number, either 0, 1, 2, 100, 20, and so on and so forth. Cannot take a fractional value, in short. Okay. Even in our illustration, our earlier illustration, the number of children in a household. So you find that the number of children will always be a whole number, and it will be a non-negative value. But there are some cases like the shoe size. Shoe sizes of students in this class. There are some cases where the shoe size is a number and a half. For instance, you may find that there are people whose shoe sizes are number 4.5. So you find that the shoe sizes takes some specific whole numbers and their corresponding halves. And that's why I mentioned that it takes some specific. So you cannot find a shoe size which is not a whole number and is not a number or a number and a half. It either takes those two formats and no other format. So the shoe size, though it does not necessarily take a whole number value, is an example of a discrete variable. Then on the other hand, we can say that a continuous variable is a quantitative variable whose data takes any numerical value within a given interval. That means it takes both whole numbers and also fractional numbers. So that's the difference between a continuous variable and a discrete variable. So that distinction will help us in understanding the difference between a discrete probability distribution and a continuous probability distribution. So examples of continuous variable are things like the height of students in a class, or maybe the time that you spend in the Zoom waiting room, and so on and so forth. So with those two distinctions, it becomes quite easy for us to differentiate between a discrete probability distribution and a continuous probability distribution. And we say that a probability distribution is said to be discrete if the variable in question is discrete. So if we are dealing with a discrete variable, then that particular probability distribution is a discrete probability distribution. For example, in this example here, in this illustration here, we were dealing with X, which was a discrete variable. It was taking some specific whole numbers or some specific numerical values. So this is an illustration of a discrete probability distribution. Okay, so if this X is a continuous variable, then the kind of probability distribution that we'll be having here will be a continuous probability distribution. So that's a simple distinction between the two types of distributions. Then after differentiating between discrete and continuous probability distributions, now we can look at examples of probability distributions. And in this class, we shall only be looking at three types of probability distributions, or three examples of probability distributions. That is the binomial distribution, the Poisson distribution, and the normal distribution. So in this class, we should be focusing on those. So those are the distributions that we shall be discussing. These two here are examples of discrete probability distributions. These ones are discrete probability distributions. And this one here is an example of continuous distribution. I also need to mention that there are many other probability distributions that will not be covered in this class, okay? But these three are quite useful in some of the data that we might be interested in finance and economics. So I also need to mention that the normal distribution is one of the most important probability, or one of the most useful probability distributions in statistics. And later on, you will realize that the binomial distribution and the Poisson distribution can be estimated using the normal distribution when some conditions are met. So the normal distribution is a very useful probability distribution. So in this class, we shall be looking at each one of them. We define each one of them. We look at the properties of each one of them. And we also look at the scenarios when it is applicable. And finally, we'll be solving some problems in each case. So let's start with binomial distribution. Binomial probability distribution. I'm sure you must have come across terms like biannual, bilateral, bisect. So when you hear the word binomial, you can imagine that there must be some two items. We don't know about what about them, but bi, then there is nomial, maybe two labels. So when we talk about a binomial experiment, this is an experiment where every trial has two possible outcomes. For instance, if you toss a coin, then there are two possible outcomes. Either head will come up or tail will come up. The gender of a child is either male or female. In quality control, when you inspect some products from the production process, then that product is either defective or not defective. So those are scenarios where binomial probability may be applied. But having two possible outcomes alone is not enough to qualify an experiment to be a binomial distribution. There are some conditions that must be satisfied, and there are four conditions that must be satisfied for any experiment to qualify to be called a binomial experiment. So that is our starting point. We're going to list the characteristics or the four conditions that must be satisfied for a given process or a given experiment to qualify to be called a binomial experiment. So we are saying that this distribution or the binomial distribution is applicable in cases where an experiment, which consists of a certain number of trials, satisfies some four conditions. And here are the conditions. Condition number one is that the number of trials must be fixed and finite. Number of trials must be fixed and finite. So fixed means that you set it in advance. As you start the experiment, you should know in advance how many trials you're going to run. For instance, you may want to say that I'm going to toss the coin 10 times. Then the number of trials also must be finite. Must be finite. That means it must be known, it must be countable. So you cannot say you are tossing the coin. If you are tossing the coin, maybe until something happens, then that's not that does not qualify the experiment to be a binomial experiment. You may say that I'm tossing the coin until I see 5 heads, then you stop. That's not binomial. So for binomial, you fix everything before you start. You say that you're going to toss the coin this number of times, and the number of times must be a finite number. So this number or the number of trials here is denoted by n. So the number of trials is usually denoted by n. For example, we can say toss a coin 10 times. So in this case, n will be 10, or the number of trials for that particular experiment will be 10. So the second condition says that every trial results in only one or the other of two possible outcomes. So in all the cases, there are two possible outcomes. And these two possible outcomes are also mutually exclusive. Remember, we say that two events, A and B, are said to be mutually exclusive if they cannot occur if they cannot both occur in the same trial, or they cannot simultaneously occur in the same trial. For example, when you toss a coin, you either get a head or a tail. You cannot get both in the same trial. So we say that the head and the tail are mutually exclusive outcomes. So it's also important to note that only one of them occurs, and there are only two possible outcomes. Then we can add that these two outcomes are usually labeled, as one of them is called the success and failure. The other one is called failure. Okay, so we label the two outcomes as success and failure. The outcome that we are interested in is the one that we call the success outcome. And the outcome that we are not interested in, or the other outcome, is called the failure outcome. For instance, if you are inspecting the quality of goods produced, and you are interested in finding out the number of defective items, then defective item or a defect is a success outcome in this case. So the words success and failure are just labels, as mentioned here. They're just labeled and labels, and they do not have literal meaning. Okay, so the outcome of interest, is assigned the label success. While the other outcome is labeled as failure. Okay, so we're saying that there are two possible outcomes like this. One of them is called the success outcome, and the other one is called the failure outcome. So this is the one that we're interested in. This one is the one that we're not interested in. Okay, then the third condition, or that must be satisfied for any distribution to be called a binomial distribution, is that the probability of the success outcome occurring remains the same throughout the experiment. It remains the same in all the trials. So that's our third condition that must be satisfied. So we're saying that the probability of success remains constant throughout the experiment. And this probability is denoted by letter P. And the probability of failure, on the other hand, is denoted by letter Q. So in other words, we are saying that the probability of success is denoted by P, while the probability of failure is denoted by letter Q. Okay. Then we note that if you take the probability of success plus the probability of failure, then you should get 1. Okay, that is the same as if you take P plus Q, you should get 1. Where this also means that if you know P, then you can get Q using this expression. If you know P, then Q is easy to know. So this feature here, or this property here, means that the outcomes, that is success and failure, are collectively exhaustive collectively exhaustive. That's why collectively means that when all of them together, if you look at all of them together, they exhaust the sample space of all the possible outcomes in this context. So that's why their probabilities are summing up to 1. Okay. Then, so that's condition number 3. Condition number 4. So the fourth property is that the outcome in every trial must be independent of the outcome in every other trial. So this is a question of independence. In other words, we're just saying that each trial is independent of all the other trials, or the outcome in every trial does not in any way, or is not in any way affected by the outcome in all the other trials. So I want to recall or to define the concept of independence as used in probabilities. So let's recall this definition that two events, A and B, they can be more than two events. But for the sake of illustration, let's consider two events, A and B, are said to be independent if the occurrence can also be or non-occurrence, of one does not in any way affect the occurrence or non-occurrence of the other. So that's what we call independence. Okay. So mathematically, we are saying that the probability of A, if this is true, that is probability of A, given that B has occurred, that's the definition of, these are conditional probability. So this means that the probability of A, if we know that B has already occurred, if that probability is the same as probability of A occurring, and the probability of B occurring, if we know that A has occurred, is the same as probability of B, then this is what implies independence. Independence of A and B. So this just means that the first statement here just means that the fact that, or the information we have about the occurrence of B does not in any way affect the occurrence of A. So the probability of A occurring, if we know that B has occurred, is just the same as probability of A. And on the other hand, we say that the probability of B occurring, if we know that A has already occurred, is the same as probability of B. So if that is true, we say that the two events, A and B, are independent. Okay. Then we can say that if A and B are independent, if these two events are independent, then the probability of both occurring, is given by, the probability of both occurring is given by probability of A, B. That's how you write it. Or you can say the probability of A and B. You can write like that. Or you can say probability of A intersection B. So this is how you denote it. But the definition is here. It is the same as probability of A times probability of B. So the probability of both events occurring is equal to the product of the individual events occurring separately. That's a definition of, or that's a formula that we use to calculate the probability of both events occurring. Okay, I want us to have a small example to illustrate that. Example, let's consider the experiment of tossing a coin. Let's say you toss a fair coin twice. So if you look at this experiment of tossing a fair coin twice, it is reasonable to believe that the first toss does not in any way affect the second toss. So it is reasonable to imagine that the two tosses are independent events. So suppose, or let's mention that NB, we can mention that the first toss is, let's say the first toss, and let's say the first toss is independent of the second, is independent of the second toss, and vice versa. So we are also saying that the second toss is also independent of the first toss. So if that is so, we can say that the probability of getting ahead in the first toss and then also getting ahead in the second toss, then this probability is the same as probability of getting ahead in the first toss multiplied by probability of getting ahead in the second toss. And this being a fair coin, we know that the probability of getting either ahead or tail is half. So this is the same as 1/2 times 1/2, which is 1/4. Okay. So if you have a scenario where, let's say this is example number 1, example 2, if you toss an unfair coin or toss a biased coin, where probability of head is 0.6, and of course, probability of tail is 0.4. Okay, so if the tosses, if the two tosses, are assumed to be independent, then the probability of getting ahead followed by a tail will be given by probability of getting ahead times probability of getting a tail, which is 0.6 times 0.4, and so on and so forth. So basically, that's how you apply the concept of independence. Now, looking at the properties, you may want to give examples of cases where binomial distribution may be applied. And the experiment of tossing a coin a given number of times is one of the best examples that you can have. Because if you decide to fix the, let's say, the number of trials to 100, then property number 1 will be satisfied. Then we know that every time you toss a coin, only one outcome will occur, that is either a head or a tail. So that will also be okay. Then the probability of getting a head or a tail does not change at any point in the experiment. And then we can argue that the tosses are independent throughout the experiment. So the experiment of tossing a coin is a simple illustration of a binomial experiment. So if you are inspecting the quality of goods of a production line, then again, you can choose the size of the sample in advance. So you can say that you are choosing 100 observations. So that is, you are fixing the size of your sample. So N will be fixed in that case. Then each trial, so every item that you inspect will also be either defective or not defective. Then moving on to the third property, you can assume or you can assign based on past experience, you can fix the probability of success or the probability of observing, let's say, a defective item. So this one can be fixed, number 3. And then you can also assume that the outcome of every trial is not affected by the previous or future trials. So again, that can pass as a binomial experiment, quality inspection of the quality of goods produced in a company, and so on and so forth. So there are many examples, as we shall see when we go to the application part. But at this moment, I want us to try and come up with a formula, to try and derive the formula that is used for the binomial distribution. Remember, we said that a probability distribution is in form of a table or a graph or a formula. Okay, so what we shall be doing here, we'll come up with a formula for the binomial distribution. And that is what we shall be using to calculate the probability of occurrence of different values of our variable of x. Okay, and we're going to do that through what we call, by conducting what we call general binomial experiments. So let's look at that, the general binomial experiment. So the experiments that, or the binomial experiments that we have looked at so far are very specific. For instance, we were saying you toss a coin 2 times, for instance. That's a very specific experiment where we also know the probability of success is a given value. So now what we want to do, we want to come up with a general experiment where we shall just let the probability of success to be a symbol like P, and the probability of failure to be Q, and the number of trials to be N. Then we try to generalize and see the formula that will give us the binomial distribution formula that we shall be using to solve some problems. So we're saying that if you consider a general experiment where each trial has just 2 possible outcomes, which are mutually exclusive, then we can denote the probability of success by letter P. And then we denote the probability of failure by letter Q. And we have mentioned that P plus Q is always equal to 1. So let's consider a general experiment, or the first trial of a general experiment. So let's have the first trial of a general experiment. The first trial. The general experiment. So the difference between what we are doing now and what we were doing earlier is that now we are just saying that probability of success is P and probability of failure is Q. Unlike in the previous case where we knew, for instance, in this case, probability of success was a half, or the probability of getting ahead, and so on and so forth. Okay. So as learned in Business Statistics 1, one easy way of displaying probabilities is the use of tree diagrams. So we can illustrate this experiment using a tree diagram like this. You can have the first trial will look like this. It will either be success or failure. So that is the first trial of the general experiment. Okay, and as we mentioned, we need to indicate the probability of each possible outcome on the tree diagram. So we said that this one is P and this is Q. Okay, so I'll be using the letter S to represent success, and I'll use letter F to represent failure. Then I want to add some columns here. So here I can have the outcome. And the outcome is either here success or failure. Okay, but now suppose I'm interested in, suppose we are interested in the number of successes. So that would be our X. Suppose now, instead of focusing on the outcome, whether the outcome is a success or failure. Suppose we are interested in the number of successes in a given number of trials. So let's include another column here where we shall put the number of successes. Number of successes. So here we just need to count the number of S's in the outcome. And in the first outcome, there is only one S. This one only. And in the second outcome, there is no S. So in this case, we would say that X is taking the values 0 and 1, the discrete variable, as you can see. Then in addition to that, we may want to have a column here indicating the probability of success. Not probability of success, probability of the outcome in question. So this is just right here, probability. So that in the first space here, we write the probability of getting a success in one trial. So we need this probability of getting S in one trial, or probability that X is equal to 1. Okay. And the probability, when you have just one trial, the probability of success is given by this. And then the probability of failure here will be given by this value here on the tree diagram. So we say that. So this will be given by P, and this will be given by Q. If you sum this, you know this will be P plus Q. And we mentioned earlier that if you take P plus Q, you'll always get 1. So theoretically, whatever the value of P or Q, we know that when you sum those, you'll get 1. So that's the first trial of a general binomial experiment. So I want us to move on to a second trial. Suppose we have 2 trials in a binomial experiment, a general experiment. So the second trial of a general binomial experiment. So again, we shall use the tree diagram, but now we have 2 sets of branches. So I'm now using S and F. So that's the first trial. Then the second trial, I'm using a different color. You can get success or failure, and here you can also get success or failure. We need to indicate the probabilities of success and failure on the tree diagram. And we said that probability of success is P, and here to be Q. And from condition number 3, right? From condition number 3, the probability of success in each trial must remain constant throughout the experiment. That means the probability on the other branches will not be changing for S and for F. So this will also be P, this will be Q. P, and this will be Q. So that's the meaning of the point, the third condition. Then just like we did in the first scenario, we can come up with this, the outcome. This is S followed by S, or SS. The outcome there is SS. Or you can have S followed by F. Or you can have F followed by S. Or finally, you can have F followed by F. Then we are interested in the number of successes. So we have number of successes. So here, you just need to count the number of S's in every outcome. So these are 2 successes. This is 1 success, 1 success, and here there is no success. So this means that your variable X, which denotes the number of successes, will be taking the values 0, 1, and 2. And finally, we indicate the probability for each possible outcome So the probability, and we're starting with probability of S followed by S. And condition number 4 says that the outcomes, so every trial is the outcome in every trial is independent of all the outcome in the other trials. So this is the same as probability of S times probability of S. And from the diagram, we know that probability of S, probability of success is P, and probability of failure, and probability of S again is P. So probability of S followed by S is P squared. Then the probability of getting S followed by F is the same as probability of S times probability of F, which is the same as P times Q, which is PQ. Then the probability of F followed by S, F followed by S is the same as probability of F times probability of S, which is the same as, again, PQ or QP, the same. Then finally, probability of F followed by F is the same as probability of F times probability of F, which is Q times Q, is Q squared. We know that if you sum these values, if you sum these probabilities, you must get 1. So we can say that if you sum P squared plus this, PQ plus PQ is 2PQ. So this would be 2PQ plus Q squared. And we know this must be equal to 1. So that's a general experiment, binomial experiment with 2 trials only. So let's try a binomial experiment with 3 trials. So let's look at the third trial of the general binomial experiment. So here our tree diagram will have 3 levels of branches. So the first set of branches, success, fail, this would be P and this would be Q. The second level of branches, success, fail, or here, success, fail, this would be P, Q, P, Q. And the third level of branches will be given by success, fail, success, fail, success, fail, or even here, success, fail. And the probabilities do not change, so this is PQ, 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 PQ. Okay. So what are the possible outcomes? The outcomes, you can get S, S, S. You can get S, S, F. You can get S, F, S. You can get S, F, F. You can get F, S, S. You can get F, S, F. You can have F, F, S. And finally, you can have F, F, F. Then again, suppose we are interested in number of successes. So in the first case, these are 3 successes, 2 successes, again 2 successes, 1 success, 2 successes, 1. I'm just counting the number of S's. This is 1 success and this is no success. So in this case, our variable X, which is the number of successes, will take 0, 1, 2, and 3, a discrete variable. Okay. Then from there, we can obtain the probability for each possible outcome. The probability of getting, so we're talking about probability of getting S, S, S. So the same as probability of S times probability of S times probability of S, which will give us, so this is the probability. So this will be P cubed. And the second one will be P squared Q. Same case with this one, P squared Q. The third one will be P Q squared. I am deliberately starting with P, yeah? Then this one will be P squared Q, followed by P Q squared. Again, P Q squared. And finally, Q cubed. So if you sum this, you will get P cubed plus P squared Q is appearing 3 times. Huh? So if I combine those three, I'll get 3 P squared Q plus, if I combine this and this and that, they are all similar. So I'll get again 3 P Q squared. And then finally, I'll have Q cubed. And I know theoretically, this must always give me 1. See, because of time and space, we cannot, will not illustrate a general experiment with 4 trials. But with these 3 trials, I want us to illustrate how we can come up with a formula that we shall be using for binomial probabilities. Yeah. So I want us to summarize this information in a table. But before I summarize, let me know if there are any questions. So let's summarize the information in this table. So when we have one trial, the expression for total probability is here. We just pick up there, P plus Q. So we have P plus Q. When we have 2 trials, the expression for total probability is this. So we have P squared plus 2PQ plus Q squared. When we have 3 trials, this is the expression. So we have P cubed plus 3P squared Q plus 3PQ squared plus Q cubed. Okay, so that's what we have. I don't know whether these kind of expressions are ringing some bells. I don't know, I'm not sure. Okay, but you will notice that the first expression here, when n is equal to 1, it is similar to taking P plus Q raised to power 1. That is what will give you this. And the second expression is similar to P plus Q raised to power 2. That's what will give you that. Then of course, the third one is P plus Q power 3. That's what will give you this. So now, is it possible for you to figure out what will happen when n is equal to 4? It's possible because we know that this will be P plus Q power 4. Then we'll have some expression here. So when n is equal to 5, we just have P plus Q raised to power 5, and so on and so forth. So our interest is the general experiment, that is when the number of trials. So our objective is to get the expression for n is equal to k trials. For n is equal to k trials. And clearly, the expression that we are looking for will be in the form P plus Q raised to power n or k, because n is equal to k. So that is the expression that we are looking for. but we need the expanded format of this formula. We need a formula which is in this format. Okay. And what you notice is that in all the expressions, starting from the first one all the way to the last one, there is a P and a Q. So even the first one, I can write the first one as a PQ plus PQ, but I play around with the powers. I say this is power 0, power 1, then this is power 0 and power 1. So this is the same as P plus Q. The second one, I can write it as P squared Q power 0 plus 2P Q. So this is power 1, then plus P power 0 Q power 2. That's the same as that. Because you know that any number raised to power 0 is 1. So this is literally a 1 like that. Huh? Okay, so even this one, this is the same as P cubed Q power 0 plus 3P power 2 Q power 1 plus 3P power 1 Q power 2 plus P power 0 Q power 3. So even as we continue, there will always be a P and a Q. And there will always be some power here and some other power here. And in addition to that, there will be a constant every time. So here there is a constant, here there is 1, here there is a 1, here there is a 1, here there is a 2, here there is a 1, here there is a 1, here there is a 3, here there is a 3, here there is a 1. So this P and Q will also be pre-multiplied by some constant here. I can call it, let me call it C. And then you notice that there is a summation of a kind. There is some summation. So the formula that we'll be looking for is of this nature. I'm not saying this is the formula, but the formula will be of this nature. It will be some summation of a constant multiplied by P raised to some power and Q raised to some power. You notice that if you add the powers of P and Q, like in this scenario, 2 plus 0, 1 plus 1, 0 plus 2, you will get 2. And this is the same as the number of trials. If you add the powers, you will get n. So in this case, this thing is in quotes. Huh? You would say that n1 plus n2 will be equal to the number of trials. Okay. So the correct format of the formula that we need to write here is as follows. So let's say the following. Huh? We say that let's have a subheading, the binomial probability formula. Binomial probability formula. We say that the probability of observing exactly X successes, this number of successes in n trials of a binomial experiment with n trials binomial experiment with n trials and probability of success equal to P is given by the probability of success of getting a certain number of successes is given by this formula. This is the formula we have been looking for. Probably that the number of successes, these are capital X, the one that we've been calling here capital X, the number of successes, probably that the number of successes is equal to some constant here is given by n. You use this item here, I'll be explaining what it is. multiply that by P power X, multiply that by Q power N minus X. So this is the formula for the binomial distribution. So this item here, the very first item here, is what I was giving the name of some constant. So this constant can be properly defined. Then this power here is what I was calling some power, some N1 and some N2, in such a way that when you add those two powers, if you take X plus N minus X, the answer is always the number of trials. Okay, so in this case, let's define each item in the formula. Where N is the number of trials. Okay, X is the number of successes. The number of successes. And the number of successes will always take the values 0, 1, all the way to N. So if there are 10 trials, then X can take the values 0, 1, 2, all the way to 10. Okay. Then P, of course, as explained earlier, is the probability of success. And Q is 1 minus P. Okay. So very important here is the item we are calling this item here. This is called combination. That's the symbol that we use for combination, which gives the number of ways, of getting X successes in N trials. So this is the coefficient of P and Q. And it gives the number of ways of choosing this number of successes in N trials. So there's a formula that can help us do this calculation. But in this class, we'll be using our calculators. We'll be using our calculators to evaluate this. For example, if you see 3 like that, this is read as, you read this as 3 combination 3. Sorry, combination 2. 3 combination 2. Or you can say, choose 2 from 3. Or the number of ways of choosing 2 objects from 3 objects. Or 2 successes from 3 trials. Okay. So I will illustrate how to use the calculator to, sorry, this is not a 3 here, this is a 2. I'm using a 2 here, not 3. So this is 3 combination 2. Or you can say choose 2 from 3. So I want us to use our calculators to evaluate this this constant. So using the calculator, like for instance, this is fx. So 82 ms. For instance, this is fx 82 ms. Sorry about that. So this is the function that we need to use. The function NCR. That is a function for combinations. Okay. So for instance, if you want to solve the example that I gave, that is 3 combination 2, you just need to press 3. You press this function, you press 2, then you press equal sign. So let's do that. So we're saying in this case, you press 3, then you press that function, that is NCR. After that, you press 2, and then you press equal sign. What do you get?
Three.
Yeah, you get 3. Yeah, so in that case, you say there are 3 ways of choosing 2 successes in 3 trials.
Yes.
There are 3 ways of choosing 2 successes from 3 trials. Okay, and I want to show you that that can be shown from the tree diagrams that we had earlier on. For instance, if you look at this larger tree diagram here, the number of trials was 3. So let's find out how many times did we get 2 successes from this tree diagram. And this is 1, 2, 3. So there are 3 ways of choosing 2 successes in 3 trials. Similarly, we can have something like this. We can also try this. Let's try 3 combination 0. That is the number of ways of choosing no success in 3 trials. The number of ways of choosing 0 successes in 3 trials. In this case, what do you get?
One.
So the answer is 1, meaning that there is only one way of choosing no success, choosing in 3 trials. Okay, and you can check from the diagram. You can check from the diagram. If you go back, you notice that no success means the number of successes is 0. And this is the only way of choosing 0 successes. Okay, so if the number of trials is larger, let's say 10, you do the same and you find that it is not easy for you to do it by hand. So that function is quite useful when the number of trials increases a bit. For small cases like these ones, you can even do this by hand. Or you can use another tool known as the Pascal's triangle, which I'm going to illustrate if time allows. So, but before we go to the Pascal's triangle, let's also try, let's try 10 combination 4. The number of ways of choosing 4 successes in 10 trials. And what do you get?
10. 210.
Sorry, how much?
210.
210. So meaning that there are 210 ways of choosing 4 successes in 10 trials, and so on and so forth. Okay. So this information can also be obtained using what you call a Pascal's triangle. Okay, and a Pascal's triangle can help you to come up with these coefficients. So the numbers that you are getting using the calculator are these constants here. These numbers. These numbers are the ones that we are getting. Like this is the number of ways of choosing 1 success in 3 trials. This is the number of ways of choosing 2 successes in 3 trials, and so on and so forth. So using the Pascal's triangle, or let me give an illustration of how the Pascal's triangle looks like. When n is equal to 0, we're talking about p plus q power 0, that is equal to 1. When n is equal to 1, we're talking about p plus q or 1, which is p plus Q. So the Pascal's triangle only contains the coefficients of the terms. So this is coefficient here is 1 and here it is 1. So this is 1 and 1. When n is equal to 2, we have P plus Q, or 2, which we saw is P squared plus 2PQ plus Q squared. So the coefficients are 1, 2, 1. So you put them 1, 2, 1. You put them in such a way that the first one is 1 and the last one is 1 in that order. Then when n is equal to 3, P plus Q is equal to P cubed plus 3P squared Q plus 3PQ squared plus Q cubed. And the coefficients are here 1, this is 3, this is 3, this is 1. So you put them here, you get 1, 3, 3, 1. So it forms what you're calling a Pascal. It can continue for very many trials. So for instance, suppose now we want to use the Pascal's triangle to give the expression when n is equal to 4. So you can just come here. You notice that these values are obtained in a very systematic way. Yeah. So at the top here we have 1, then we have these 2 1s. Okay. Then all the other rows are obtained from this row. So the first value must be 1, and the last one must be 1. The middle value here is given by this number plus this gives you 2. So that's when n is equal to 2. When n is equal to 3, the first one must be a 1, the last one must be a 1. So this number 3 here is given by this plus that. Okay. And also the other 3 is given by 2 plus 1. Get that. So if you have 4 trials, you will start with a 1, you will end with a 1. So the values in between are 1 plus 1, 1 plus 3, which is 4, 3 plus 3, which is 6, 3 plus 1, which is 4. And you will notice that, so those are the coefficients. You will notice that the powers of P are always increasing. They are always increasing from, this is 3 here is the value of n. And here, this is the same as n, even here. So the powers of n are increasing from the value of, they are always decreasing from n all the way to 0. So this is 3, 2, 1, and here there is a p power 0. Maybe this is a better expression here. So the powers of here, the powers of p starting from the first one are decreasing from 1, which is the number of trials, to 0. And the powers of q are increasing from 0 all the way to n. Same case here, p, 2, 1, 0. And then q starts from 0 to 1 to 2. Here, p starts from 3, 2, 1, 0. And q, 0, 2, 0, 1, 2, and 3. Then the coefficients here are obtained from the Pascal's triangle. So with that in mind, I can just come here and say that this will be the same as, I know there will be a PQ, this will be power 4, power 0, plus P power 3, Q power 1, plus, I'll put the coefficients later, P power 2, Q power 2, plus P power 1, Q power 3, plus P power 0, Q power 4. Then the coefficients are from the Pascal's triangle. This is a 1, this is a 4, this is a 6, this is a 4, this is a 1. So this is the same as P plus Q power 4. Of course, you can simplify this by removing this case and this case to remain with P power 4 plus 4P cubed Q power 1 plus 6P squared Q squared plus 4P Q power 3 plus Q power 4. So that's how you can use the Pascal's triangle to get expanded form of all these. But the most important thing in the whole of this story is this formula. This is the formula that we shall be using in the application of binomial probabilities. So if you want to calculate the probability that X takes a certain value, and here we're talking about exactly a given number of successes. That's why we have an equal sign here. For instance, we shall be talking about probability that X takes the value 3. So how do we get that? We shall use that probability depending on N, depending on P. Because for the binomial distribution, two things must be known for you to move on. The value of N, that's the number of trials, and the probability of success. So guys, I want us to stop there for today. In the next class, we shall be looking at now the application of binomial problems or binomial distribution to solve some problems. Any questions?